This DP Physics summary video about topic 8.1 energy sources. Now, in the guide, you're meant to distinguish between primary and secondary energy sources. Well, what is a primary energy source? It's something which can be found in nature, which has not been processed in any way. For example, you have the fossil fuels, crude oil, coal, natural gas, but also solar and wind are primary energy sources, whereas secondary energy sources have been processed in some way. For example, mechanical energy and electrical energy. There are also two different terms to do with energy that you're meant to know. One is specific energy and the other one is energy density. Now, whenever we hear the word specific in physics, it refers to per unit mass. So it's the amount of energy per unit mass, or joules per kilogram. Energy density, however, is the amount of energy per unit volume, or joules per cubic meter, Jm to the -3. And one of the positive things about fossil fuels is that they have a high energy density. They have a lot of energy per unit volume. Now, there are two types of energy sources. One is non-renewable and the other one is renewable, which we talk about a lot today in today's society. Non-renewables are finite, which means they will one day run out, and you might have heard of the term peak oil. And therefore they are depleted much faster than they can be produced. Some examples of non-renewables are oil, natural gas, coal, and uranium. The renewable energies will last as long as the sun shines, because the sun is the major source behind, well, pretty much all renewables apart from geothermal. Some examples of renewables are solar, wind, and water. But still, according to 2010 statistics, they only make up a small part of today's energy supply. Fossil fuels in 2010 made up about 80% of the world's energy consumption. So, fossil fuels, how do we get energy from them? Coal, oil, and gas are examples of fossil fuels. They've been created over millions of years, and they are traditionally the way we have generated electricity. However, they do contribute to something called the enhanced greenhouse effect, which we'll go through in 8.2. The energy changes which are going on there are chemical to thermal to kinetic to electrical, where you have the fossil fuel being burned, water getting turned to steam, which turns turbines, rotating coils, and a generator to generate electricity. And they are sufficient losses. Often a coal-fired power station is about 40% efficient. You have and this is a very simple schematic of a power station, fossil fuel power station. Sankey diagrams, you have to know and understand, are a way of showing of the energy you put in, for example, of 100 joules of energy you put in, how much useful energy you get out in terms of electrical energy. So, for example, 20 joules would be lost in the boiler, 40 joules would be lost in the condenser, 5 to the generator, and only 35 ends up as useful energy. So to work out the efficiency, we take the useful energy out, 35, divided by the total energy in, which is the 100. So this power plant would be 35% efficient. And these arrows bending down, most oftenly bending down, are losses, represent the losses in the power plant. However, a nuclear power station works slightly differently. You do have water being turned into steam, which turns turbines and generates electricity. However, you have in the reactor, you have fuel rods in black here, control rods in blue, which can be raised up and down, and around here you have the moderator. In the whole system, though, you have pressurized water which gets heated up and then cools down and gets pumped back around again. So this is a typical reaction in a nuclear power station. You have neutron capture, and then you have these products being produced. But the important thing is you have more neutrons produced than you require to put in the reaction. So you have a chain reaction. These two neutrons then go on to produce two more reactions in turn. However, you need a so-called critical mass of uranium in order for the neutrons not to escape the reactor itself. Energy is made by the fact that fast neutrons are captured and their kinetic energy is turned into thermal energy, and it's the role of the moderator to slow down the neutrons and therefore convert that kinetic energy to thermal energy. So the collisions increase the temperature of the moderator, generating energy or converting thermal or kinetic energy to thermal energy, which then gets turned into electricity via turbines, as in a fossil fuel power plant. However, there's another important element of the nuclear power station. That's the control rods, which can be raised up and down. Their job is to control the rate of reaction, how fast or slow the reaction occurs. So if you lower the control rods, you decrease the rate of reaction. Raising the control rods will increase the rate of reaction. Of course, there are advantages and disadvantages for fossil fuels and nuclear, and I won't list them here, but if you want to, you can pause and read them for yourself. But the role of nuclear is actually being discussed now, and there's a possibility of having more small-scale nuclear power stations, which does have advantages over the old, larger ones. However, that's mainly a research stage as we are speaking. In terms of the renewables, one very much up and coming is solar. Traditionally, solar panels would have used light energy to convert arriving on a black surface here, which would heat up the black surface and then heat up water pipes, pumping them around the system, and you could then store the heat energy in a boiler tank or tank. However, what's happening nowadays is photovoltaic cells produce electricity directly from sunlight, and the efficiency is improving by year on year, and right now the maximum efficiency is about 30%. What happens is you have the photons incident on the cells, releasing electrons and generating a potential difference which can be used to power electrical devices. Another common, at least in the Swedish context, common renewable power supply is the hydroelectric. That's where you have a mass of water dropping a certain height h, turning a turbine, and then generating electrical energy. So basically the energy conversions is gravitational potential to kinetic to electrical. So if we have the density equation, density is mass over volume, and the power equation, power is energy divided by time. The power is the change in gravitational potential energy, mgh, over a change in time, which we can call delta t. To get the mass of the water that falls a height h, we use the mass from the density equation. And because we don't have a constant volume, we have a changing volume per unit time, we can use mass equals rho times delta V, where delta V is the change in volume of the water. So we get the power equation to be rho delta V GH over delta T, and often times you'll find that the rate of change of volume with time is given the quantity Q, which is the volume flow rate. However, the IB diploma program syllabus explicitly states you have to know about a pumped hydroelectric system. Basically, you store the water in a reservoir. You have a reservoir at the bottom of a hill and a reservoir at the top of the hill, and at peak times the reservoir or the water from the top is released down the hill, turning the turbine, and then ends up in the reservoir at the bottom of the hill. Then at night the water is pumped back up again when the electricity is cheap, to be stored at the top of the hill again. That's what we call a pumped hydroelectric system. Wind power is also very popular here in Scandinavia. Basically uses the fact that a mass of air basically has a lot of kinetic energy, which we can use to turn a turbine, then therefore generating electricity. The kinetic energy of the air, half mv squared, can be expressed as, because the mass of the air is rho v again, and the volume of the air is basically the volume of this cylinder of air. If the cylinder travels a distance v delta t, and the surface area which cuts the blades is a, then the mass of air turning the blades is rho a v delta t. Substituting this m into the kinetic energy formula gives a half rho a v delta t v squared, which means that the kinetic energy contained in this column of air is proportional to the cube of the wind speed, and it's also proportional to the surface area of the propeller, which is in itself proportional to the square of the radius of one of these blades. So the power generated, or the amount of energy per unit time, is a half rho, which is the air density, times A, which is the cross-sectional area of the blades, times by the wind speed to the power 3. So an example calculation here using these values means that for a typical 30-meter wind turbine at 8 meters per second wind velocity, we have a power of 800 kilowatts, although modern day wind stations are a lot more powerful than that. Again, I won't go in depth into this slide. You can stop it and pause it and read for yourself. But basically, we'll list some advantages and disadvantages of all these renewable energy sources. Basically, one of the main advantages with solar, hydro and wind, when we say clean, is that they do not contribute to the enhanced greenhouse effect, i.e. they do not contribute to global warming. And that was the end of this summary video. Hope you liked it. Please give me a thumb up and subscribe. Thank you.